Good morning. We are back, and we are going to head on into Chapter 34. We have a couple lectures on this. Chapter 34 and 35, and we kind of talked about this at the end of the last lecture. We're going to start looking at light a little bit differently. So rather than just some beam of something traveling through wherever, light is made up of particles. Light's made up of photons, and as kind of like analogous to the materials around us, are made out of electrons, protons, neutrons, and I'm going to throw neutrinos in there. In any case, we're now going to start talking about the particle makeup of light. Now, all the particles in nature have what are called wave properties, also referred to as phase properties. When we say light is a wave, it's really misleading. Physicists, when they say light is a wave, they mean something very different from, I think, the way people interpret what they're trying to say. So we're going to have to be more clear about what these wave properties are for light and for other particles. Electrons, protons, neutrons, photons, they've all got wave properties to them. And fortunately, we have a lot of the semester left. We're going to be able to look at that in a fair amount of detail. We're going to need to in order to get you guys through the course, because as, engineers or scientists of this day and age, you have to understand what the properties are of these particles. So anyway, chapter 34 is referred to as the wave nature of light, and that corresponds to this effect called interference, and chapter 35 is going to be kind of more of the same. So these two chapters are going to be pretty closely related. So here's a list of the units, and usually I kind of skip through these pretty fast, but I just want to start going in, and you can do the same thing in the textbook if you want to. If you've got a textbook, you could start crossing things out if you want. Or you don't have to. You don't have to cross stuff out. But anyway, every time you see something that says wave versus particles, I just want to get rid of that. There's kind of this idea, is light, is it a wave or a particle? And I think it's a mistake to tell light what it has to be. It either has to behave like this or it has to behave like this. It's absolutely established that light is made out of these elementary pieces, these elementary particles of light. So they're photons. Now, there are certainly wave properties that are taking place. And again, we'll see how that works. So I think a better way to view this is, hey, light is made out of particles. They're called photons. And these particles have wave properties to them. That's it. So no more of this obsession over, what's going on here. Let's go in and see what these wave properties are like. Now, classically, Christian Huygens from, 300 years ago, back in the time of Newton, was studying light and how it propagated and established many of the wave properties of light. Now, at the time, it wasn't understood that light consisted of these fundamental particles, but we'll find out how these two ideas fit together. So Christian Huygens was able to explain refraction, reflection, and interference effects. Young ended up doing a series of experiments. This brings us into like 1800, something like that. So maybe 100 years later, a series of interference examples. We're going to take a look and see what that means. And then we're going to look at what's called a double slit interference effect. That's kind of the standard starting point to try and understand what interference of light and what the wave properties really end up leading to. And it's kind of interesting. And then we're going to look at interference effects in thin layers of material. It turns out that thin layers like bubbles, when you look at bubbles, there are color bands in them. Those are interference effects. If you look at a layer of water with maybe a little bit of oil, a thin layer of oil across the top, and you can see all those different colors, that's actually coming from an interference effect. We'll get a chance to go in and look at that and understand that also. All right, so what is this Huygens principle? Well, light consists of particles. We call those photons. I'm gonna put this on every slide, so I'm gonna really drive this point home. And these photons have wave properties to them. Now, again, going back 300 years to the time of Newton, Huygens' principle said this: if you start with a light source, light will tend to radiate away from that source, and one way to understand how the light's propagating is to treat each new region of light as if it's each point along that is starting a new radiative effect. Okay, so that's what this diagram is trying to show. Once the light reaches this wave front, so these are called wave fronts. Once the light reaches this particular location, well, this wave front can be thought of as propagating, each point along it is propagating 180 degrees, or in a half sphere away from that point. And when you combine all the interference effects, what it does is it says that this will generate an additional wave front. So this is kind of a principle that you can state in words, and what we're going to end up doing is replacing that with some mathematics. So we'll have some mathematical formulas that are the mathematical expression. They're actually based on quantum mechanics, but what we're going to find is that those mathematical expressions match the ideas that Huygens was writing down from his observations with light. So now we feel like, physics is always trying to get a better understanding of how things work, but we feel like we have a pretty good understanding of how what light consists of and what its properties are, and how to understand that. So again, I couldn't help sliding this in. I think I'm saying the same thing over and over, but photons, no, I guess this is a new idea here. Photons don't just follow one path. So this is one of the features of quantum mechanics, is that a particle like an electron, or a neutron, or a proton, or a photon, they're not located at just one point. And they don't follow a very specified trajectory. Now, when you see a beam of light, you're thinking, hey, yeah, but I can shine this light, and all the light, isn't it just following this one path? If we take a close look at that path of light, what we find is that the photons inside there are actually spread out across the beam. So an individual photon actually has many different ways that it could be following the path. When we see the light coming from a beam of light, it's because those photons now are interacting with molecules along the way, and we're seeing it's kind of mapping out all the possible locations that each photon could be traveling. So that's a little crazy, but that, all the evidence is that that's the way nature works. So from this source, if I've got a photon spreading out, an individual photon could have all of these paths available to it. At some point, the photon interacts with something, it gets absorbed by some material, and then it gets absorbed at one location. So this is referred to as collapse of the wave function. If you've heard that, that's what we're headed towards. If you haven't heard it, it's not a big deal. So no worries. We're gonna get to this stuff when we get to it. So let me move on from this. So this is what people have seen for hundreds of years, running these light experiments. And again, particles with wave properties. If we take a sample of light, it looks like it just goes in a straight line. But if we set up a barrier and remove part of the light, what we can see are these sideways effects. So what looked like light that was just traveling in a forward direction, all of a sudden is going sideways. Well, how do we understand that? And Huygens suggested, and quantum mechanics kind of agrees with this, that as an individual photon, each individual particle of light is spread out. So individual photons know about the barrier, and an individual photon knows about all these regions out here. So a photon comes in, you know, there's a 50% chance it gets blocked by the barrier. But half of the paths available to that photon actually go out and around this. Now, once you're around this path, the paths that we're heading in this direction are no longer interfered with. What was keeping these middle regions from spreading out was the presence of surrounding paths. Once this set of paths is gone, now we see that with that set of paths gone, this side begins to spread out. Now, what's interesting with this, and this is one of the things that Huygens looked at, is that as the opening in the barrier gets narrower and narrower, you start to see the spreading become more and more pronounced in the limit of the width becoming really, really narrow. So in the limit of becoming infinitely narrow, what we find is that light that looked like it was going straight ahead is now spreading out kind of uniformly in all directions. Now, most of the light's getting blocked by the barrier. So in order to see this effect of an individual point and having light spread out away from that point uniformly, we have to remove the surrounding portions of the light paths. So those light paths are eliminated by the barrier, and then we can say, oh, photon left to itself could go in any direction if we bring that down to a narrow opening. So this effect is referred to as diffraction. This is a little more complicated, so we're going to save that for chapter 35. All right, I'm going to take us back all the way to chapter 31.4. I was told that everyone in the class passed Physics 4B, so congratulations. I'm glad that you guys all passed Physics 4B, but that means I get to use stuff from Physics 4B here, right? So this is a slide that I took back from chapter 31, last chapter that was covered in Physics 4B. It's talking about electromagnetic waves. Now I've got three different terms I have to keep track of. So what is light? What is an electromagnetic wave? And what are photons? And they're all the same thing. So what we want to do is go back and look at chapter 31. Now, what we've got, what I'm going to do is take the slide from chapter 31, which shows the propagation of an electromagnetic field. So the electromagnetic field, in this case, the electric field, is in the vertical orientation along the y-axis, and the magnetic field is always perpendicular to that. So we've got electric and magnetic fields that are perpendicular to each other, and then they're mutually perpendicular to the direction of motion of the light. Okay, so first of all, what does this have to do with light and where are the photons? So back in chapter 31, we said this is light. Now, when we use the word light, we're talking about a broad range of spectrum. We're not just talking about visible light. We're thinking infrared, microwave, radio, and in the other direction towards higher energy, we're looking at ultraviolet, we're looking at X-rays and gamma rays. So this picture really fits in best with an antenna. So I'm going to put an antenna in here and say, here is my antenna. It's broadcasting a signal. It's broadcasting a radio signal. That radio signal consists of a lot of photons. Now, the photons that are being generated, each individual photon has a little tiny electric field and a little tiny magnetic field oriented kind of like in this diagram. So this diagram is going to work fine for that purpose. Now, the total electric and magnetic field propagating away from this antenna comes from adding together all of the electric and magnetic fields of all the photons that make up that radio signal. Okay. Now, why does it have the pattern it has? Is the electric field here, the magnitude of the electric field varies from location to location. Now, this is where the word wave becomes dangerous. I always say showing this diagram is the most dangerous thing I do in any of my classes, because unfortunately, I'm guessing in a lot of your science classes, they just keep saying everything's a wave. But I don't feel like they ever really tell us what a wave is. So let's think about that. First of all, is there anything here that's following this curvy path? And you go, no, there's nothing following that curvy path. What this diagram is showing is that if I look at the propagation of this radio signal, let's say we follow a path away from the antenna. So I'm going to follow that central path. This diagram is telling us what the electric and magnetic field magnitude will be at each location. Now this is one of the dangerous things with vectors. When we use vectors, there's kind of an intuition that somehow the vector extends over that space, and it doesn't. The magnitude of this E field is just saying at that point, the E field has a certain number. And at this point it has a different number, and at this point it has a different number, and here the E field is 0, and here it's got a negative value, and here it's negative. So rather than drawing it this way, which looks really cool, and fits in with this idea of, oh cool, everything is wavy, what they should really replace this with are just a series of numbers. 0, 10, 17, 25, 17, what did I say? 10, 0, minus 10. So we should just stay along that path and not follow the curvy one. Okay. So again, the electromagnetic field, nothing is doing this. Okay. It's not wavy. So what a wave corresponds to, and we talked about this in Physics 4a, and we talked about this in Physics 4b if you're in my classes, was that a wave is just saying that there's some sort of a propagation effect. Something is propagating in a matter where something is propagating away from a source. Now what does happen with this antenna is that you're generating all these photons. Photons carry energy and momentum, and they are traveling away from the antenna. Now in terms of electric and magnetic field, we can go in and measure the combined electric and magnetic field of all those photons. That's what we measure when we're measuring the electric and magnetic field at different locations. But there's nothing doing the wave here. Okay? There is a propagation effect. Photons are spreading out. Now if I chose a different path, maybe I choose a path up here or here at different locations from this antenna, and along those paths, what we're ending up with is the same idea. Just at every location in space, there is a number and an orientation for the electric field. There is a number and an orientation for the magnetic field. Okay, so wave, when you hear the word wave, you've got to think very differently than I feel like you've been taught to do in a lot of science classes. And maybe not. Maybe your science classes have been on track with this, but I feel like this is one of the most common misconceptions we have in physics, in science, and it's reinforced. I think a lot of science teaching reinforces this incorrect view of how we understand light. Now, the reason that the electric fields have these differing values to them, I guess I better go along here and not follow that wavy path. The reason the electric field has different values for an antenna is because in the antenna we have an AC current. We have electrons being oscillated back and forth. So the electrons are speeding up and slowing down, speeding up and slowing down, speeding up and slowing down, and they're changing directions. Now, if you remember that, again, if you took my class in Physics 4b, we talked about the acceleration fields. So if charged objects, like electrons, are accelerating, they will generate a particular shaped electric field, and that's what we've got here. So the antenna has a bunch of accelerating electrons, and that value of acceleration keeps changing, and as it propagates away from the antenna, what these values for the electric and magnetic field at each location corresponds to what the acceleration of the electrons were at that particular instant. So that pattern of accelerations shows up in the varying electric and magnetic field. So when we say that the electric and magnetic field are sign functions, so here's the way it gets represented. This is from chapter 31, but we're going to see the same thing here in chapter 34. We use, here is an amplitude, a magnitude, and then here is this sine function, and this represents a propagation. So here is the wave number, here is the angular frequency, and this whole effect is propagating away. The reason it has this shape is not because light is a wave. The reason it has this shape is because the antenna that generated it had an acceleration of its electrons the acceleration was behaving like a sine function. Okay? If the electron's acceleration was behaving differently, this pattern of electric and magnetic fields would be whatever the pattern was for the acceleration of those electrons. If that pattern were not sine and cosine functions, the electric fields would not look like sines and cosine functions as you follow them when they're propagating away from the antenna. Okay, so one student a few years back in Physics 4C said, okay, I get it. So waves can either be wavy or non-wavy, and I think that's it. So when we use the word wave, all it's saying is something is propagating, doesn't say anything about the shape. The waves can look wavy, like sines and cosines, or the waves can look non-wavy. Waves can look like other functions. Okay, so we don't want to get too attached to these sine and cosine functions. Now, phases depend on location and time. Here is the wave number related to the wavelength. Here is the angular frequency related to the frequency. And then the frequency times the wavelength for a propagating something can be written as omega over the wave number, which is the velocity. If these are electromagnetic fields, that field, that pattern is propagating at the speed of light, and the reason why is because photons are massless. Special relativity will be there in a couple chapters, shows us or predicts that any particles that are massless are always traveling at the speed of light. They can't slow down, they can't speed up. Unlike other particles, if particles do have mass, then they can be found to have a range of different velocities, but not for massless particles. Okay, so why does light travel at the speed of light? Because photons are massless. All right, so here it is. Here's quantum physics. I got a couple slides I threw in here. It's a lot of the same stuff we already talked about. I'm going to refer to it as quantum physics a lot. It's also just referred to as quantum mechanics. The two basic principles are all of nature, everything we see consists of fundamental units, which we call particles. Now, particles are not like marbles. Particles are dynamic. Particles have these dynamic properties to them. So a particle, a fundamental particle, an electron, a proton, a photon, a neutron, they don't follow just one definite path. There's a range of possible paths they can follow. And along those paths, they have this property called phase. And so let's see if we got this. Everything is made out of fundamental particles. The properties all have wave or phase properties to them. Okay. Here's my particle list. There are protons and neutrons. Now, protons and neutrons you guys are familiar with. You know protons and neutrons from your chemistry classes. And protons and neutrons are very closely related particles. And so, checking the clock here. Protons and neutrons are closely related particles. They have almost the same mass. In fact, what we're going to find is that the proton is the charged version of the neutron and vice versa. The neutron is the neutral version of the proton. Now, in the same way that the proton and neutron are kind of the same particle, there's a neutral version of the electron. It's called a neutrino. Now, you don't hear much about neutrinos, and that's because neutrinos don't interact with other materials very much. When we generate neutrinos, they don't have much of an effect. And so there's a good chance you've gotten through your entire scientific educational career up until now without ever hearing about neutrinos. But just, to make a nice symmetry here, electrons are to neutrinos as protons are to neutrons. Now, the other particle that we're going to be looking at is photons. Now, it's not a comprehensive particle list. We'll see that not till near the end of the semester. We'll look in more detail. So for most of the semester, we're going to take those 5 particles and say, hey, those are our fundamental particles. We want to follow their properties. So, for example, here's an electron. I drew a little circle, even though it's not a marble. What are you going to draw it like? So here's an electron headed off in some direction. This is the symbol for a photon. So a photon, we use the Greek letter gamma. You've heard of gamma rays. Gamma rays are photons. And so that symbol became associated with photons in general. So just the same way we can follow the propagation of an electron, we can follow the propagation of a photon. And in going from point A to point B, electrons, photons, whatever fundamental particle we're looking at, they can follow many different paths. It's not just a straight shot from point A to point B. And that says that we're going to represent them by what are called wave functions. The wave functions are keeping track of, there's a constant, at least in the case where these particles are just what we call free particles. If they're free particles propagating through space, the wave functions can, in many cases, be represented as some kind of a constant times an exponential to a complex phase. Now, if you've taken differential equations, I'm guessing, and looked at solutions to differential equations, you know that sines and cosines, oscillatory functions, can be represented instead using complex exponentials. We use the E, the E 2.7128, whatever that number is. Boy, that's a fundamental number in math. Kind of like pi. Pi is this remarkable number that shows up everywhere, not just in circles. Well, E is another number that shows up everywhere. And it turns out that in quantum mechanics, in order to follow a particle and propagate it, sines and cosine functions are okay, but using exponentials is better. It has a better set of mathematical properties. Who would have guessed when you learned complex numbers back in your algebra classes when you were solving the quadratic equation, right? Maybe that's the first time you were introduced to the square root of 1. It turns out that once you introduce I, the square root of 1, the set of complex numbers has a lot better properties to it mathematically than if I is excluded. If you ignore imaginary numbers, you find out that certain mathematical operations have no solution. What is the square root of 175? Negative 100, sorry. What is the square root of negative 175? Well, once you introduce I, all the operations become closed. And so a mathematician might suggest, oh, wouldn't it be wonderful if nature were based on the complex set of numbers and not on the real numbers? And it turns out quantum mechanics does that. So quantum mechanics is not based on exclusively real numbers. We use imaginary complex numbers to represent what's going on in nature. It's kind of interesting, kind of fascinating. So anyway, we'll bring this up a few more times. Let me do this. As long as we're here, let me talk a little bit about the properties of photons. Photons have no mass, as far as we know. We've measured this really, 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 really carefully. And if they do have mass, it's really, 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 really tiny mass that they have. But they do have energy. So each individual photon has energy, has a certain amount of linear momentum. Photons, individual photons, also have angular momentum. Now, when you think about it, that's not so much of a surprise because electrons are the same, right? If we ran this list, well, electrons do have mass. They have energy, they have linear momentum. Electrons have angular momentum a little bit. You know from your physical science classes or chemistry, electrons can be what we call spin up or spin down. right? Two possible spin states. Well, spin represents an intrinsic angular momentum. So each individual electron has a little bit of a fixed amount of angular momentum, and it can be spinning in one of two different directions. Photons are the same. Photons have more, they have a full unit of angular momentum. Electrons only have a half unit. But also for photons, there's two possible spin directions. Okay, who knew, right? That's kind of interesting. So, and that's it. We say once we've identified those properties, that's the exhaustive list of properties for a photon or an electron. That's what their properties are. And so in quantum mechanics, we're going to be using complex numbers to represent how particles get from one place to the other. Just a quick look at how the phases compare. Now I wrote phase as if it's this whole piece. We could also just say the phase is the stuff that's up in here. It's the kx minus omega t that we saw in physics 4a and physics 4b. We've used that expression before. And that represents something that's traveling in a particular direction. And now what we're going to do is we're going to bring in the quantum physics relationships that say that the frequency of a particle depends on what its energy is. And the wave number of a particle depends on what its momentum is. Now these are divided through by h bar, which is what we call Planck's constant. Now I didn't write that down. Again, we're gonna get back into this. So I just wanted to give enough of an overview in quantum mechanics that we could approach chapters 34 and 35 in a quantum mechanical approach, rather than textbooks kind of do this. Textbooks tend to, we've kind of gotten ourselves in the habit of presenting the quantum physics of light differently than the quantum physics of other particles. But I want to show that, hey, there's just one approach, and it works for all the particles. Okay, so frequencies depend on energy, wave numbers or wavelengths depend on the momentum of the particle. So here's light propagating. Now, this was the approach that we used back in physics 4b, and we said these are plane waves, and what this represents is a region of space, and in that region of space we've got light propagating through. This is a three-dimensional attempt. I'm not sure if it was successful. So I tried a side view and said if I've got light propagating through a three-dimensional space, then I have what are called wave fronts. And at all locations along the wave front, the phase of that function is the same. So the phase varies from location to location, but it varies from one plane to the next as to what the phase is. Now, again, the quantum mechanical approach would be, rather than using sine functions, turns out if we use sine functions, sines and cosine functions to represent a photon or an electron is not what's called an energy or momentum quantum state. Sine and cosine functions are combinations of different quantum states. It turns out that the pure quantum state is given by these complex exponentials. So this is kind of our default wave function to represent a photon, and it's going to replace these E's and B's. And the textbook's using these E's and B's, and that's fine. And you can kind of understand what's going on with the E's and B's. But eventually, we're going to get into using, and the textbook is too, into using these wave functions. The Greek letter here we're using is psi, P-S-I. And it's kind of a squiggle with a line through it. But that's what this symbol is, P-S-I, psi. So this is a quantum approach to representing paths of light. Okay, one more page on complex numbers. From your math classes, I'm hoping you remember Euler's formula. Euler's formula says e to the I anything. So u is our variable here. If I take and exponentiate I times a variable, times anything, it's going to be cosine of u plus I times sine of u. Now that seems remarkable, but when you go in and study complex numbers, which I'm guessing you've all looked at complex numbers to a certain extent. Hopefully in your differential equations class, you've looked at them in more detail, and that these sorts of formulas are familiar. But again, in any case, it's not essential right now that you become expert at these complex numbers, but start to get used to the idea of that is what we're going to be using to represent. And it's weird because when you bring in complex numbers, things that have imaginary and real components, it's like, well, how do I imagine this? Because how do I imagine imaginary space versus real space? So it is weird that we use these. All right, so the wave function we're using, which we say is this guy, is a combination of a real portion that's behaving like a cosine and an imaginary portion that's behaving like a sine. And it turns out that this particular mathematical representation corresponds to a photon with a definite amount of energy and a definite amount of momentum. So what I'm going to do is I'm going to concentrate on this part, the kx minus omega t. I'm going to call that the phase and say in shorthand notation, when a particle's traveling, we can represent it as some constant times e to the I times this phase. Well, I just kind of rewritten Euler's equation here. There are what are called phase diagrams. So what happens on a phase diagram is instead of a cosine function that oscillates back and forth or a sine function that oscillates back and forth, when we do a phase diagram of this complex exponential, that's equivalent to having something follow a circular trajectory in the complex plane where the real portion, a cosine phi, is a projection onto the real axis, and the imaginary portion, a sine phi, is a projection onto the imaginary axis. Okay, so I'm hoping you guys think of this as it's kind of cool. We're going into a little more detail. Again, you're going to be fine. Don't panic. If this is not necessarily making a lot of sense, it's not essential. Okay, so you guys are going to be fine through this. All right, if we go back and take a look at refraction. So let's go back and take a look at refraction. Here is light coming in towards that air-water boundary. Now what we realize is that individual photons, as they approach the water, they're not just following one path. So an individual photon could be a combination of this path, and this path, and this path, and this path, and this one. And what that says is that this path doesn't reach the water as quickly as this path does. This path hit the water first. Now when it hits the water, that particular path of the photon starts interacting with the water molecules. You go, wait, isn't it the photon that interacts with the water molecules? And you go, well, this path, along this path, we have to consider that at this point, it's slowed down, whereas this part of the photon's representation has not slowed down yet. Really? Is that how it works? So what's going to happen, and all the experiments indicate it does. So what's going to happen is each of these possible paths for our photon is going to hit the water at a different time. And that means it will all slow down at different time locations, okay, points in time. What that does is, how many of you guys were in marching band in high school? See a raise of hands there. I always suggest this should be a prerequisite for the course. Because if you're in marching band, you learn how refraction works, right? If you're in marching band and everybody's marching in these nice lines across the field, how do you turn the band? And what has to happen is that column by column, if you want to turn the band, then column by column, the ones on the inside of the turn have to slow down, the ones on the outside have to keep moving. So what happens is, column by column, this one slows down, and then this one slows down, and then this one slows down. And what happens is, instead of having these nice parallel wave fronts, now the wavefront gets tipped. And once everything is tipped, then everybody can do a turn and come out of that, and then you're back in a wavefront again. So see how everybody's lined up here, 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 and then these different columns have to slow down, but not until they hit the water. And since they're all hitting the water at different times, what that will lead to is this particular wavefront. And then this particular wavefront, sorry, these guys have slowed down. These guys have continued going at full speed. When you regroup on the other side, where everybody now is in the water, then you can march off as a wavefront, and everything lines up again. Okay. Who knew that photons and electrons and protons, they all took marching band in high school. So they all know how to do this. And so what we can do is we can do some calculations here now. This diagram, again, they've drawn this really well, and that's why I wanted to show this. But they didn't do all the math. Let me show what's happening. Let's see, everybody's lined up right until this path hits point A. And then this one slows down, whereas this path hits point D at a later time. Well, by the time this path has hit point D, point A, the light has moved on to point C. Now, A to C is not as long as B to D, and that's because here the light has slowed down. Here it was going at full speed. So what we can do is we can do geometry on this. What we can do is we can take this triangle, triangle ABD, and compare it with triangle ACD, and they share hypotenuses. It's two right triangles. They share a hypotenuse, but they're not similar. And that's because this side is longer than that side. But what we do know about those two sides is they both took the same amount of time. It took the same amount of time for light to travel from B to D as it took for this path of light to travel from A to C. So if I take into consideration all the different possible paths the light could travel, I predict the refraction effect. Let's see if we can come up with the formula from that, taking a look at that diagram. So here we are. Here are the wavefronts coming in. Here is D, which is the distance of the hypotenuse. I'm calling this side D1, which is V1 times T, where V1 is the speed of light in this medium. So this medium is N1, this medium is N2, and in medium N1, the N1 is going to equal C over the speed of light, and in medium N2, N is going to equal C over, the speed of light, C over the speed of light in this material. So what we can do then is take a look at these two paths that we had concentrated on. I'm going to call this D1. I'm going to call this D2. This is D1 is equal to V1 times T. So during the time interval T, this path traveled a shorter distance. So this is V2 times T. This is V1 times T. But the T's match. And so that says that if I do trigonometry here, sine 1 is D1 over D. Sine 2 is D2 over D. Sine 1 over sine 2 is equal to D1 over D2. That's V1 over V2. The T's cancel. So what I'm left with is sine 1 over sine 2, which is V1 over V2. So the ratios of the sines equal the ratios of the speeds of light through those materials. And then that gets replaced by the index of refraction. There it is. The law of refraction. We didn't just make that up. So now we have a way, using quantum mechanics, to derive how the refraction, the law of refraction, came about. Okay, and so this is just kind of a repeat here. This is just stating the same thing that we just went over So it's just restating that this Huygens principle can be used to explain the law of refraction. And what we're seeing is that parallel to the Huygens expression is this new approach, quantum mechanics, where instead of the propagation of some wave, what it is individual particles with wave properties instead. So individual particles have this effect to them. Okay, I think, yeah, so basically it's just a summary, a conclusion that what we did is working. This is their derivation, which looks pretty much the same. I filled in a few more steps, but basically that's the idea. Here they are using the idea of wavelengths to express what's going on. Okay. Another effect that we can understand with this is mirages on the highway. On the left they've got this picture. You guys have seen this. It's a hot day and you look down at the highway and you go, oh my gosh, the highway's gone. It's covered with water. Why is the highway shimmering? And that's because when you look down at where the highway is, you're not seeing the highway. What you're seeing instead is light passing through the air. Now what happens is when you have a hot day and you've got a highway with pavement, that pavement absorbs a lot of light. It becomes very high temperature and it creates a temperature gradient in the region near the surface of the pavement. And that means that the air very close is very, it's really high temperature. And so that air heats up more. If you know the sunlight coming into the earth, the sunlight passes mostly through the air, is absorbed by the surface, and then the atmosphere is mostly heated from the surface, not from the light coming through. So the atmosphere is mostly heated from the infrared coming off the surface. So we have air that's superheated right here, and as the air goes into that, the speed changes, right? It's the same as refraction. As it goes into less dense air, the air near the surface now is less dense, and what happens is this light travels faster, the light over here travels slower, and those differences, again, marching band, if one side is going faster and the other guy is going slower, you're going to curve. So this refraction effect doesn't have to be a distinct boundary. It can be a gradual variation of the index of refraction in a material, and in this case, the index of refraction of the air near the surface is lower. And that bends the light away from the pavement. So the light you're seeing here is actually coming from up above. It's coming from the cars or even from the sky. And that's what gives it that shimmering effect. All right, we're going to move on to kind of a classic example here. And we do have a few more minutes. I just keep checking the time here. So let me get this introduced, and then next lecture we'll pick up with this. You guys may have heard of the double slit experiment, and if you haven't, that's fine. I want to let you guys know, I didn't take physics in high school. When I did take physics in college, it was my freshman year. I was a chemistry major, and physics was one of the requirements. And that was really my first introduction to physics. So I wasn't familiar with a lot of the jargon that was used in physics. And so anyway, if you guys haven't heard it, it's fine. What we're going to do is we're going to look at an effect called interference. Interference specifically says, look, if we have different paths that the light's taking, how do we decide where the light's going to end up if it's taking different paths? Now, the simplest way to look at this would be to pick two paths. So what we're going to do is this. We're going to take a barrier and we're going to send a beam of light. Now, a beam of light still means that it has a width to it. So we're going to send some light towards this barrier, and it's going to have a certain width to it. and the light is going to spread out over 2 slits. Now, you may be thinking, maybe you're not, why don't we just use 2 pinpoints of light? And it turns out slits are easier to work with mathematically. So what we're going to do is this. We're going to say that the light's coming through these 2 slits, and then here is a viewing screen. Now there's a couple of possible outcomes of what could happen. First of all, there is the straight line path prediction, which is wrong. The straight line path prediction says, look, wherever light gets through the barrier, it's going to keep traveling in a straight path. And that says that when we look at the viewing screen, there's going to be 2 bright regions that represent the slits. Now, if you have big sources of light, this is kind of what you see. But if we can get the slits down to where they're kind of the same order of magnitude as the wavelength of the light, those paths of light are narrow enough that we'll start to see that diffraction effect that we talked about. So the light actually will spread significantly if we can get those slits narrow, and that's what we do. So the title here talks about Young's double slit experiments. These were done around 1800, and what Young found was if you did these narrow slits, you got these crazy patterns. You got what we call interference patterns. So instead of a light looking like the barrier it went through, you get a series of different bright regions. Now, this isn't the best representation, so we're going to see some better representations. It's not such distinct bands. What there is a rise and fall in the intensity of the light. So the light gets more intense and less intense and more intense and less intense. And that pattern doesn't look like our 2 slits at all. So what's going on here? Now, this is the interference effect prediction. That's the quantum mechanics prediction. Quantum mechanics says that if a particle is able to take many different paths, when those paths come together, where the particle eventually ends up, we have to take interference effects into account. The paths will have different phases to them, and depending on whether the phases match up or they oppose each other, we'll have high intensity or low intensity at that location. Okay, so that's kind of the basis. And so this is a good diagram too, and we'll probably stop here for the day. But so let's take a look. Here is slit number 1, here is slit number 2. This is, fairly narrow here, and this is fairly narrow. So here is the light coming in, and remember, each individual photon is possibly traveling all of those paths together. So what this says is most of the paths terminate on the barrier. The barrier absorbs most of the light. So most of the photons end up being absorbed. But there's a chance a couple of the paths of the photon travel through the slit. So there are paths that go through slit 1, and there's a path that goes through slit 2. Now once you've made it through 1 and 2, the light now is going to spread out so it can travel in any possible direction. Same thing here. And what we'll end up with is interference effects over on this side, and the interference effects consist of the combined effect of the 2 paths. We have to add the 2 paths together. Now, there's 2 possible paths to any location on the screen. So if I'm trying to find out what's going to happen right here on the screen, I got to follow these 2 paths and count the number of wavelengths. And by counting the number of wavelengths, I'm going to be able to decide are the paths in phase or out of phase. And I think we're running out of time in this. I don't want this to go over, so I'm going to wrap this up right now, and we'll start from here after the break.